Okay, so in the last video, we introduced our friend the curl and saw that he was incredibly useful for determining whether or not a force field was conservative, namely if the curl is zero, it is. So here we can take a look at this guy here. This was the force field I had on the previous example, or on the previous video. You can see it's got a very definite counterclockwise swirl to it, and the curl is non-zero. Now what might be a little less obvious is looking at this guy here. I think you can convince yourself if you're on either of the major diagonals that the curl is zero. If I stick, say, a water wheel right here, the paddles will be hit equally hard on either side. But it turns out that's actually zero everywhere. If, say, I stick it here, yeah, it's getting hit a little harder down here, but there's more of it curling in more perpendicular to the paddle wheels here and here, and that turns out to be just enough to cancel it out to keep the paddle wheel from churning. So I can't imagine what force in nature this would be, but if there were such a force, it would be conservative. You can get a few other examples here of things that just look weird. For instance, this guy here, I go and take a look at him, you can see that if I were to stick a paddle wheel in here, it wouldn't want to churn anywhere that I stuck it, and sure enough the curl is zero, so such a force would be conservative. By the same token though, if I just, with this particular example here, I've got a strange exponential whose y component here depends on the value of y. But here, if I make the y component of the vector depend on the value of the x coordinate, it turns out that here the curl is non-zero. It's some sort of utterly hideous thing. Yes, 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 right, exactly at x equals 0. The curl is 0. But in general, if I get off of it, you'll see that here the paddle wheel wants to spin clockwise. Sure enough, a negative z component there. And then over here, it wants to spin counterclockwise. I stick in a minus x there. Minus and minus gives me a plus. Sure enough, a positive z component there. So that matches up. So even though, symmetry alone isn't a guide to whether a force is conservative or not. This one and this one are both symmetric. This is conservative. That one isn't. This and this both have some sort of bizarre symmetries to them, but this one is not conservative. That one is. Okay, we'll hold that thought for a moment here while we go to develop a little more stuff. So I'm going to work a little more on developing potential energy further. So what I'm going to contend is that we should be able to write any valid potential energy should give me the force if I operate a gradient on it. So I need to do a bunch of stuff here. First off, I need to give us the idea of what the gradient of a scalar function is. So what I'm going to do is we're going to operate the gradient on some scalar function. Let's just call it I don't know, v. That would be I hat partial v partial x plus j hat partial v partial y plus k hat partial v partial z. So what this is saying is we take the partial derivative of v with respect to x, that's the x component of the gradient, same with y, same with z. I have plotted out here on Mathematica, I went ahead and did a contour plot of the sine of the product of x and y. And so you can see here as you're looking at the numbers, 0.1, 0.2, 0.3, and so forth. We get to a maximum right there, and then we start dropping back down. And if I take the gradient of the sine of xy, we see that it basically is telling us how to point uphill. The steeper uphill you're going, so you're crossing through contours rapidly here, you get a big vector. The steeper you're going, the bigger the vector. The less steep you're going, see big spacing between contours there. The shorter the vectors are over here. So that's how we go about interpreting that. If we want our potential energy, if we want our function v to be the potential energy, then what we need is for the force to equal the negative of the gradient of the potential energy, because the forces want us to go from high potential energy to low. Now, so the question is such a force conservative? Well, there's one way to find out, and that's to take the curl of it. Now we can go ahead and pop that into Mathematica like I did right there. I took the curl of the gradient of the sine, and I got 0 identically. Here, by the way, is the gradient of the sine of xy for those of you keeping score at home. So Mathematica at least assures us that, yeah, the force is conservative. But I think it's probably instructive if we go ahead and do it for ourselves. So we'll take the curl of f, and that would be the curl of the negative gradient of v. Well, we can pull the minus sign out, so this becomes the negative of the curl of the gradient of v. So now let's go ahead and find it. So this will be equal to the negative of I, j, k, partial x, partial y, partial z. Then here for the xyz components, this will be partial v, partial x, partial v, partial y, partial v, partial z. All right, so let's go ahead and take that derivative. So that's the negative of, let's get the I hat part. It'll be partial y of partial v, partial z, minus partial z of partial v, partial y. So we write those as partial squared v, partial y, partial z, minus partial squared v, partial z, partial y. And there's a spiffy theorem that was second order partial derivatives. You can interchange the order of partial derivative taking, so they cancel. Similarly, if you go ahead and do the y and the z, you'll see that those terms go to 0 as well. So sure enough, the whole thing is the null vector. So any force that can be written as minus grad v is conservative, and vice versa. And it turns out, I'll just assert that they prove in vector calc that there are no other such conservative forces. So, following along with that thought, let's say if f is conservative, we already know that, see, the integral from a to b of f dot dr, so that's the work, that'll be equal to the negative of the integral from a to b of grad v dot dr. And so we can go ahead and do this out slotwise. This turns out to be minus integral ax to bx of partial v partial x dx minus, same thing with y's, minus the same thing with z's. Okay. And we can kind of put that all back together and say that that's the integral from minus a to b of just plain dv evaluated at r. So this is minus the change in the potential energy, or minus v at b minus v at a, like we'd advertised a lot earlier. So what we have is integral a to b f dot dr is the change in the, that was, we already saw before, the change in the kinetic energy. That's also equal to the negative of the change in the potential energy. So I can rewrite as delta t plus delta v equals 0, or I can take that thought and say, well, that's t at b minus t at a plus v at b minus v at a equals 0, or I can rewrite that as t at a plus v at a equals t at b plus v at b equals some sort of constant that we'll just call E. That constant, of course, is the total mechanical energy. All right, so you might wonder, what do we do if there are non-conservative forces present? In that case, what we do is we separate our forces. So we go ahead and say integral a to b of, now let's say f plus f prime dotted with dr equals delta t. Now this f here is the conservative force, and the force or forces, and the f prime are the non-conservative force or forces. Okay, so we can break that out into two pieces. That will be equal to integral a to b of f dotted with dr, which is something we already understand, plus integral a to b of f prime dotted with dr. Okay, so we get that delta t will be equal to minus delta v, that's what that term is, plus we're just left with integral a to b f prime dotted with dr. So this is one of the versions of the work energy theorem. It says that the work done by non-conservative forces, and that we have, since it's non-conservative, we will have to explicitly calculate it for the path in question. There's no way around that. Is equal to the change in kinetic plus the change in potential energy, or we can say is equal to the change in the total mechanical energy. All right. So for that example that I touched on a little earlier, where the potential energy was some function of the sine of x the product of x and y. Let's let the potential energy be equal to some constant to make the units work, times the sine of the product of x and y. Let's go ahead and find the force and verify that it's conservative. So the force would be equal to the negative of the gradient of v. So there's no k, there's nothing along the z direction because there's no dependence in z, so the partial derivative with respect to z will be 0. So we're just left with, let's see, derivative sine is equal to the cosine, so we'll have a minus, we can pull out a k, we'll have an I hat times sine of x, we'll have cosine of xy times derivative of what's inside, leaves me with a y, so IY cos xy, and actually we're going to have a cos xy from the other one as well, so we'll just hold our horses there. Differentiating with respect to y is going to give me a x sine xy, so plus j hat x, and I'll have a cos xy. So that's my force. All right. So let's go ahead and take the curl. So curl of f, well, I can go and pull the minus sign out immediately. And so we've got I, j, k. I can pull the k out too. No need to muck with that. Partial x, partial y, partial z. And then here, I already pulled the k out. I'll have a y cos xy, x cos xy, 0. All right, so let's go ahead and take that. Well, again here, if we do this one here, that's 0 that way. We're just taking partial derivative of 0. We go like this. We're going to be taking the z derivative, something that doesn't depend on that, so nothing along x. Same for y. We take the z derivative of something that depends on x and y, so it's 0. And we take the x derivative of 0, so that's 0. So the only thing we have left is in the k hat direction. So we'll have a minus k hat times this constant k times, let's see, we'll have a partial x of this guy here, so that will give me cosine xy plus x derivative cosine is minus the sine. So let me make that a minus there, minus the sine, and then taking the derivative of what's inside, it's going to give me a y, so minus xy sine of xy, and then minus partial y of that, so that is going to give me minus cosine xy minus we'll get a derivative of cosine minus the sine, so c plus xy sine xy. Yay! It's 0. So sure enough, the force in question is indeed conservative, and I have no clue where you would ever find it in nature, but it sure is a neat example. Okay, so next time we will pick up on analyzing situations involving separable forces, and then take a look at a bunch of different examples, ending up finally with studying constraints.